Boa tarde, bem-vindas e bem-vindos ao colóquio Gleb Vatagen do Instituto de Física. Eu vou pedir para o professor Raul Abramo, que é o presidente da nossa comissão de pós-graduação, dar as boas-vindas ao colóquio Gleb Vatagen e em seguida eu volto para apresentar o nosso palestrante.
Obrigado, Paulo. Eu sou Raul Abramo, o presidente da comissão de pós-graduação e queria dar as boas-vindas a todos. O colóquio Gleb Vatagen foi iniciado há 5 anos atrás e traz sempre um convidado especial para não só dar um colóquio, mas para também ter uma sessão de bate-papo com os estudantes de pós-graduação. E aqui está uma selfie do bate-papo de hoje, com algumas das pessoas que estavam lá, e está aqui o Bill Phillips aqui, e a foto à direita aqui é o do Gleb Vatagen, que vocês todos conhecem, que formou basicamente a primeira e as primeiras gerações de físicos e a quem a gente deve boa parte do começo da física no Brasil e no Instituto de Física. Também queria aproveitar para dar as notícias de que a gente vai ter um colóquio Gleb Vatagen bem na abertura do primeiro semestre do ano que vem, no dia 24 de março, com o convidado que será o professor Neil Turok, o diretor do Perimeter Institute, e a gente vai ter mais uma sessão com bate-papo e o colóquio também. Mas agora eu vou passar de volta para o Paulo, que vai fazer a introdução do Dr. Bill Phillips.
Okay, thank you, Raul, and I'm switching to English as a matter of courtesy because as many times Bill Phillips has been to Brazil, I don't think he understands Portuguese yet. So we're still working on that. It is, of course, a huge privilege and always an honor to be able to announce another regular speaker in our colloquia. And of course, you must all have read that Bill Phillips received the Nobel Prize in Physics in 1997. So it's a very distinguished speaker. But I would like to actually emphasize the human aspect. Bill is extremely accessible, has always been an extremely accessible person, loves to chat about science, loves to both answer and also ask very penetrating questions. So it's always a huge pleasure just to be able to be around him and to be able to talk to him and learn from him. In this morning's session, unfortunately, I was not able to really fully enjoy the session, but I caught parts of it. And our students really had a very nice interaction with him. I would like to emphasize one question that I heard and his answer. And the question was about an aspect of Bill that everybody who has the privilege of meeting him at conferences, and I've had that privilege quite a few times, knows that he is always the champion in asking questions at every talk. So the question was a little bit about how he does to ask so many questions and, what's the secret. And there are 2 aspects to the secret. One is that he's always taking notes. So I would encourage you all to take notes in his talk today and, try to put in practice the strategy so as to ask him questions. They will be most welcome. He already told us that if you want us to interrupt, whenever there's a question, we can interrupt the talk. The second part is actually very telling about his character. And it's not just after receiving the Nobel Prize, it's before receiving the Nobel Prize. One of the things Bill said was that he was never afraid to ask questions because people could think that he was stupid. Now, this is a Nobel laureate who is saying, I'm not afraid to look stupid. And he actually added that, he considers himself stupid, which is absolute nonsense. But he actually added that. And I think this is a great value of the kind of scientist that is a role model for our young people. And so I'm very happy that he honored us with his presence and all his being availability for this talk today. So without further ado, Bill Phillips.
Thank you, Paulo. Thank you, Raul. It's a pleasure to be here. Thank you for that very kind introduction. Now, somehow or other, I've got to figure out how to share my screen again. Let's see. Let's hope that this works. Okay, I think that works. You're seeing a title slide?
Yes.
Okay,
Yes.
Great. So I'm going to talk about the recent reform of the International System of Units, what we call the modern metric system. Just to reiterate, I'm from a place called the Joint Quantum Institute, which is joint between the National Institute for Standards and Technology and the University of Maryland. And at NIST, I'm part of the laser cooling and trapping group, even though I won't be saying very much about laser cooling and trapping today. And my group leader is Gretchen Campbell, and she leads a group consisting of Paul Lett, Trey Porto, Ian Spielman, Ida Tietzinger, Charles Clark, and Nicole Younger-Halpern. And it's a pleasure for me to be able to interact with them and their young people. So besides NIST, I'm also representing the International Union of Pure and Applied Physics. I'm also remembering that IUPAP recently held its general, well, recently, a few years ago, held its general meeting in Sao Paulo, and that was a wonderful occasion. But Commission C2 of IUPAP has responsibility for things like symbols and units and measurement. And so as a member of that group, I'm trying to spread the word about the reform of the International System of Units. And I want to emphasize what's already been said. Please ask questions. Okay, so what is this revolutionary reform, quantum reform of the International System of Units? Well, on the 20th of May, 2019, which is World Metrology Day, we experienced the greatest revolution in units of measurement since the French Revolution, which brought us the metric system. And the nature of that revolution is that today, the International System of Units, this system whose symbol you see here, that has 7 base units, the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela. All of our measurements are made in terms of these base units. Today, as a result of the quantum reform, every one of those units is defined by fixing the value of a constant of nature. Now, in order to understand how it's possible to define units of measure by fixing the value of a constant of nature, I would like to give you, with my apologies to the late, great Stephen Hawking, a brief history of time. Because time is a unit of measure that has evolved over time and is and has been for many decades now been defined the unit of time by fixing a value of a constant of nature. So let's think about history. Historically, 1 second is a fixed fraction of a day. 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. So 1 second is 1 day over 86,400. Now, the trouble with that definition, which is very clear and probably the one that almost everyone thinks of as being the definition of a second today, is that we've known for more than 100 years that the length of the day is not constant. And it's not just the kind of seasonal variations that occur in the length of the solar day, but the tides slow down the rotation of the Earth. Earthquakes redistribute the mass of the Earth, changing its moment of inertia. And all these things produce changes, some regular, some random, in the rotation rate of the Earth. And so, because we had clocks that were good enough, here's an example of one of those clocks. This is the first atomic clock, 1949, at the National Bureau of Standards in the United States, the ancestor of NIST, where I work now. This was the first atomic clock. It wasn't an atomic clock. In fact, it was a molecular clock. It used ammonia as the standard of time. A quantum transition in the ammonia molecule is what was used as the ticker for this atomic clock. Once you had clocks like this, whose constancy was much better than the rotation of the Earth, it was clear that the definition of the second, based on the rotation of the Earth, is inadequate. You have ways of measuring time that are better than the very definition. Here's a slightly later clock, the Caesium clock from 1955. Today, the ticking of cesium atoms is still the definition of time. This is a very simplified version of how it works. You imagine a cesium atom with a nucleus and a valence electron. It's in some particular energy state, and you shine in microwave radiation at about 9 gigahertz. And if it's just the right frequency, and that frequency is written here, then it makes the electron flip its spin. That changes the energy of the atom from some lower state represented here to some higher state represented here, higher in energy by Planck's constant times this frequency. If the frequency is not just right, then it will not make the atom change its state. And so the basic way in which an atomic clock works is you adjust the frequency of the microwaves until it's making the electron flip its spin, and then you know that the frequency of the microwaves is equal to this number. So that's how an atomic clock works. And as of 1960, the definition of a second was still the definition based on the rotation of the Earth, but you had clocks like atomic clocks, whose technology was more than a decade old. And so it became clear that we needed to redefine what we meant by a second. And so in 1960, they redefined the second to be a fraction of the year 1900. What were they thinking? It's true that the year 1900 never changes, but it's also not very readily available to measure today. Well, astronomers are very good at extrapolating, and so they could figure out how long the year 1900 was, but it wasn't very convenient. And so finally, in 1967, the General Conference on Weights and Measures changed the definition of the second to be based on atomic time. And the definition of the second then and now is that it's the duration of some 9 billion periods of the radiation that corresponds to this spin flip transition in the ground state of cesium. And ever since the first atomic clocks were made, and since the redefinition, the atomic clocks have been getting better. And this plot shows that the atomic clocks have been getting better exponentially, because this is a log plot of accuracy versus time. However, the clocks got to be about part 10 to the 14 and didn't improve very much. And the reason for that was that the cesium atoms are moving so fast. The cesium atoms are moving at a few hundred meters per second, and it's simply hard to measure things that are moving that fast. They don't stay in the apparatus very long. There are Doppler shifts and other kinds of relativistic shifts in the frequency, all of which limit the performance of the cesium clock. I and my group have been involved in work learning how to make those cesium atoms and other atoms move more slowly, laser cooling. And laser cooling has produced atoms that are as cold as 1/1,000,000th of a degree above absolute zero. And this has allowed atomic clocks at NIST and elsewhere in the world to operate about 2 orders of magnitude better than the best atomic clocks before laser cooling. So now atomic clocks are operating at parts in 10 to the 16, and we can see the continued improvement in the performance of atomic clocks on this graph was due in large part to laser cooling. And here's a picture of one of those atomic clocks. This is an atomic clock at NIST, the laboratories in Boulder, Colorado. This is Don Meekoff and Steve Jeffords, and they cool a cloud of cesium atoms down to a temperature on the order of 1/1,000,000th of a degree above absolute zero. They launch the atoms up in the vacuum about 1 meter high, and the atoms fall back down after about 1 second. And this very long observation time is one of the key features that allows clocks like this to have this incredible accuracy of a few parts in 10 to the 16. And in fact,
Bill, we have a question here from Manfredo, who is actually the director of the Institute. And he's asking, Bill, for an atomic clock, you need a hell of a counter, better than a nanosecond counting time. Is that right?
Yeah, well, that's right. And modern counters can, in fact, count frequencies that fast. Before we had frequencies that were that fast, people would use various tricks to make measurements of frequencies. That is, they would take two higher frequencies and beat them against each other down to a lower frequency that could then be counted. But today, fast electronics can count these kinds of frequencies directly. Now, it's a very interesting point, though. I'll get to it a little bit later, but today, the best clocks oscillate at optical frequencies, and we cannot count optical frequencies directly. And so it's been very important to develop techniques for measuring optical frequencies where we can't, in fact, count these frequencies. So it's a really good point, and something that we very much have to take into account today. Okay, so it turns out that today time is the most accurately measured quantity in the International System of Units, and in large part that's because we have such things as atomic clocks that can tell us what a second is to such incredible accuracy. So here's a key concept that I want to emphasize: that we started with time being defined in terms of something that's rather arbitrary, the rotation of the Earth. Nothing guarantees that the rotation of the Earth will stay constant, and in fact, we know that it doesn't. And that artifact has been replaced with something having to do with a quantum transition of an atom, something that we believe is unchanging with time. It's interesting that in the 19th century, people like Kelvin and Maxwell already had this idea that it would be better to use something like an atomic standard than to use an artifact as the standard of measurement. In fact, it was Maxwell talking about a standard of length rather than a standard of time. He says such a standard that would be based on atoms, the wavelength emitted by atoms, and we'll talk about that in a moment, rather than changes in the, rather than something based on the dimensions of the Earth, is exactly what you should do. And he is joking a little bit. He said, anybody who expects their writings to be more permanent than the Earth itself had better express their results in some kind of atomic units. Well, anyway, let's stop and have any questions that anyone might have about time. And I've even suggested a few possible questions, but I'm happy to hear any questions that you might have and try to answer them.
Feel free to ask any questions to Bill at any time, by the way.
Yeah,
just
anytime.
Reiterating.
But we'll stop right now and hope to get a few.
Bill, I'll hop in.
Sure.
I heard you once describe in wonderful terms the Ramsey technique
Hmm.
to measure time, in terms of a first interrogation and then checking whether it was still correct. Could you elaborate on that? Maybe it would be helpful.
Sure. I'm just wondering whether I even have any slides that say anything about the Ramsey technique, but yes, I'll be happy to say something about. So Ramsey, and Ramsey is a very important person in my own life, because Norman Ramsey is my academic grandfather. He is the thesis advisor of my thesis advisor. And in 1949, he came up with a kind of a trick for measuring atomic frequencies better than the standard way. And it's a technique that essentially all atomic clocks use today. And it's a technique that is used really widely in atomic physics. It's used in information processing these days. Anyway, here's the idea. You start off with an atom in a particular state. Maybe I can go back to my cartoon of how the atomic clock works, but this is the oversimplified version. So you start off with an atom in this state, okay? And you shine in microwaves for a short period of time. And the response of the atom to that short burst of microwaves is to go into what we call a quantum mechanical superposition of this state and the other state, the state to which the microwaves are driving the atoms. And then the microwaves turn off, and the atom now evolves in the dark. And because the atom is not in one energy state or the other, what happens is that its state evolves at the frequency difference that corresponds to the energy difference between these two states. You could think of it as being that this electron is precessing around. Instead of pointing up or pointing down, as shown in this cartoon, it's going around. It's going around at exactly this frequency, assuming that the cesium atom is in a vacuum and free of a magnetic field. Then it's going around at exactly this frequency. And then sometime later, you turn on the microwaves again. And depending upon where this electron spin is pointing, when the microwaves come back on, they might drive it back to the ground state, or they might drive it back, continuing on to the excited state. And then you measure, where are the atoms? Are they in the excited state, or are they in the ground state? And the beauty of this technique is that the longer that you wait, the more precise this measurement is. Because let's say you wait enough time that the atom has this electron spin has turned around 1,000,000 times, then you're going to automatically be within a part in a million of the right result. If you wait a whole second, which we now do, you'll be within a part in a billion. And then by making more careful measurements, you can get to a part in 10 to the 6th of that. And that's why these clocks are so good. That's why these clocks are good to a part in 10 to the 16. So I don't know, without some extra pictures, I wish I had included some extra pictures on here. It's hard for me to do as good a job as I might have liked, but that's the general idea. You allow the atom to tick many, many, many times, and then when you put on that last burst of microwaves, it's basically seeing where, in the ticks, you know how many ticks it made, and now you want to know what the fractional tick is, and that's what that last burst of microwaves does. And as a result, you can make these measurements incredibly accurately.
Bill, so you asked for questions, you have questions. So from YouTube, we have 2 questions here. So one of them is from Tiago, is asking, what was the idea that was behind you coming to this frequency of 9.162 blah, blah, blah gigahertz?
Yeah, right.
So,
yeah. Very good. Very good. I love that. Whenever we make a change in the definition of any unit, we strive to make that change in such a way that no one will notice. So what was done when that particular frequency was chosen as the new defined value, what was done was we took the best measurement of the cesium frequency using the old definition of the second, the one that was based on the year 1900. So we took that best the best measurement based on the old definition, and then fixed the value of the frequency to be that best measurement. So now it's no longer something that's measured because it's a fixed number, but we fixed it to be the thing that we'd measured before using the old definition. In that way, there's never any jump, so that people won't be disconcerted by having the units of measurement changed. Now, there's an interesting story that goes along with that. They messed up when they did the redefinition in 1960. They wanted to redefine the second in terms of the length of the year 1900. They did it by averaging the mean solar day over a number of years, beginning at the present time, that is the time 1960, and going back a fair number of years. I forget how long. But since the Earth had been slowing down during that time, what it meant was that the new definition was not consistent with the current value of the mean solar day. And it was because of that that atomic time is a little bit out of sync with astronomical time. And as a result, we have to have leap seconds every so often to make astronomical time and atomic time stay in sync with each other. So they messed up for just the reason, just on this point that the question raises. They didn't make the definition of the second continuous from the mean solar day to the year 1900, but they did make it continuous when they changed to atomic time.
Great, Bill. So we have another question from YouTube, then another on Zoom, then another on YouTube. At some point, we'll have to go back to your presentation. But now Carlos from YouTube is asking, is it possible to create more precise clocks with other elements? If not, why? And why specifically Cesium-133?
Okay, so let's start with the second question, why cesium was chosen in the 1960s. Really, first started in the 1950s. Cesium has a number of wonderful properties. It's the heaviest of the non-radioactive alkalis. Well, actually, rubidium is very slightly radioactive, but let's not worry about that. And as a result, it has the highest hyperfine frequency. Now, this is good because if you've got anything that disturbs the frequency, like a magnetic field, by a reasonably constant amount that would be the same for the different alkalis, it's a smaller fractional shift for cesium than it would be, say, for hydrogen or for sodium or for lithium. And so having that high frequency is good. The vapor pressure of cesium is quite high. So that means you don't have to heat it up very much to get lots of atoms. If you heated it up, the atoms would be moving more rapidly, and that would be bad. In addition, because it's so heavy, that means for a given temperature, the atoms aren't moving as fast. So that's good also. And another thing, which we don't have to worry about today, is that in 1950, we didn't have lasers, so we didn't have the convenient way that we have today of detecting cesium atoms. Today, we just shine a laser onto the cesium atoms at the right wavelength, and the cesium atoms light up, and we can see that they're there. In the 1950s, a different technique was used called surface ionization. The valence electron of cesium is easy to pull off. And so if a cesium atom comes in contact with a metal surface like tungsten, where the work function of the tungsten requires a lot of energy to pull an electron out of the tungsten, it means that the electron wants to be inside the tungsten because that's where its energy would be lowest. So the electron is pulled off of the the cesium atom into the tungsten, and that leaves a cesium ion, which is easy to detect. So that ease of detection was very important for the choice of cesium. Today, it's also a great atom because it's very easy to laser cool it. The only thing that's wrong with cesium is that collisions between cold cesium atoms shift the clock frequency more than some other atoms. But everything else about cesium is great. Okay, so that was why cesium. Okay, so the first part of the question was, what about the future? And the future is that we will have to get rid of cesium, because right now we are able to measure, when I say we, I mean the community is able to measure the frequency of other transitions in other atoms more accurately than it's possible to measure the cesium frequency. So it's routine in laboratories all over the world to measure optical transitions. So not microwave transitions, which is what cesium is, around 9 gigahertz, but optical transitions, which are close to 10 to the 15 hertz. And it is possible to measure these frequencies to parts in 10 to the 17th, parts in 10 to the 18, and even better. And so we will be redefining the second once everyone agrees on what the best new atom is. So thank you for that question. That was great.
Excellent. So we have a question from Marcelo Terra Cunha now. Marcelo, just turn on your mic and please go ahead.
Thank you. Good to see you again, Bill. I will quite get the second question you suggest about general relativity and ask, is the definition of the second related to the cesium atom in the vacuum, or can we use them on Earth with some relativistic effects? And what's the precise definition and how we tune to it?
By the way, before you answer, Bill, because we have other questions related to this, you provoked people with the general relativity effect, and we have another question on YouTube, which is also about general relativity, and I understand also Paulo wants to ask something about that. So if you can elaborate a bit more about the general relativistic effects, this is something that lots of people are asking also.
Okay, so in 1915, Einstein came up with his theory of general relativity, his theory of gravity. And one of the things that came from that theory was that a clock is going to run slower if it's deeper in a gravitational potential. So that means that a clock at sea level will run slower than a clock up on top of a mountain. Now, the effect is not very big, depending on what kind of a clock you have. The effect is about a part in 10 to the 16 per meter. So that means if your clocks are only good to a few parts in 10 to the 16, as long as you know where you are within a few meters, everything is fine. And it's not very difficult to know where you are within a few meters. But if your clocks are good to a part in 10 to the 18, then you have to know where you are within a centimeter. And that's not so easy to know what your elevation is. And it's not really your elevation that counts, it's the gravitational potential. So for example, if you wanted to compare a clock in Boulder, Colorado, which is right next to the mountains, to a clock in Sao Paulo, which is close to the sea, this is not going to be very easy because we don't really know enough about the composition of the mountains and the density of the rocks in the mountains to be able to make the correction for the gravitational potential. So this is a problem. But let's come back to what is the definition. So I gave you the definition. It's, that a second is equal to so many periods of the cesium atom, but that's the simple version of the definition. There's a longer version of the definition that includes what we call the mise en pratique, the putting into practice of the definition. And that tells us a few extra things, like where should the clock be? And right now, the clock is defined to be the cesium frequency at mean sea level, at a gravitational equipotential that corresponds to mean sea level. Now, you realize this is going to be a problem because the sea level is changing. The distribution of mass on the Earth is changing. We're taking mass from the polar ice caps and redistributing it into the oceans. And this is going to change the gravitational potential. So what is the correct definition for the future? Right now, we have a definition which is like the old definition of the second. It's something that is not a very good definition, not at parts intended of the 18. So some people have suggested that we should have a definition based on a position at some place out in space somewhere. I don't know what the right answer to this question is, and we'll certainly have to think about it very carefully. You also asked about in the vacuum. Well, the third question here has to do with that. Black body radiation produces what we might call a light shift on the frequency of the cesium atom. The fact that the cesium atom is bathed in thermal radiation at room temperature changes its frequency. If you were to enclose the cesium atom, and people do this, in some kind of a thermal shield kept at a temperature of, say, liquid nitrogen, you get a different frequency. So what is the definition? The definition specifies 0 Kelvin environment. So that means that we have to make a correction for the black body radiation at room temperature. We know how to make those corrections if you can guarantee that the temperature of your apparatus is uniform, and if you measure it carefully, and if you're sure that your atom isn't seeing anything that's at a different temperature, then you can make these corrections. People have both calculated them and measured them. But of course, this gets harder and harder as you get more and more accurate. So these are questions which, when I came to NIST in 1978, were not relevant questions. But today they are very relevant questions because of the tremendous improvements in atomic clocks.
Okay, Bill, we have a last question very briefly from Paulo. Paulo, go ahead.
So, Bill, I'm going to be brief, but I don't know whether you will be able to be brief. Most likely not. Just related to these questions about general relativistic effects, clocks, even if they're based on atoms, eventually they will have finite dimensions, right? Do you believe in a fundamental limit to these dimensions? And why are dimensions important? Because eventually your clock will be in the presence of some inhomogeneous field, right? Some inhomogeneous gravitational field, which will obviously affect the definition of time. So do you believe that there is a minimum size or some kind of limit in terms of the size of the clock towards the measurement of time and the definition of the second?
Well, so we're already facing this kind of an issue. Optical clocks with atoms and optical lattices are now so good that you can tell the difference between the bottom part of the atomic sample and the top part of the atomic sample. So we're not talking about the bottom and top of an atom yet, but the fraction of a millimeter difference between the bottom of where the atomic sample is and the top of where the atomic sample is can be measured. But as long as we can measure it, we can deal with it. Now, what you're asking is, what if we get down to the point that we can measure things so well that the gravitational potential difference between the bottom of the atom's wave function and the top of the atom's wave function might be an issue? I mean, that's a really wonderful thing to think about. My guess is that if that were the only issue, then we would probably define the time to be the correct average. And since it's linear with distance, and since on the Earth, the potential is pretty much linear, it's not so hard to say where the middle is. But my guess is that we will have more problems than that first. But who knows? Maybe sometime in the future, long after both of us are dead, people will be able to measure time so accurately that we'll have to worry about it. It probably won't be the size of the atom in the sense of the size of the electronic wave function. It will probably be the size of the atom in terms of its center of mass wave function in whatever trap it's held in. And of course, we can make that tighter and tighter, but probably we will not, because the shifts that will result from trapping it will also come in. So there's lots of interesting things to think about, and I haven't thought about most of them. Okay.
Excellent. So we are all out of questions, Bill. You can continue your
and this is wonderful. I mean, I love these questions, but we might not actually get to the meat of the of the talk if we keep going like this, but it's great. Okay, so now I'm going to try to go quickly through this. There's another story having to do with length. And, length was originally used, the standards of length were originally based on the human body. A fabric merchant would sell you fabric based on how long his arms were. Well, this wasn't very good because it's not very consistent from one fabric merchant to another. Or say if someone's building a building, different size builders would be inconsistent. You can't tolerate that. And so what people did was they specified not just a person in general, but a particular person. Often it was the king or the monarch, the pharaoh in ancient Egypt. And in ancient Egypt, the royal cubit was based on the size of the pharaoh's forearm. But the pharaoh wasn't always around. So what they did was they made an artifact. They made a piece of stone that was the length of the pharaoh's forearm. And they used that to make the measurements that they needed in building the pyramids. And the result was that the pyramids are really, really good. They were recalibrating their field standards. The baselines of the pyramids are accurate to a small fraction of a percent. They're square to 12 arc seconds. They really used this metrology technique to make very good measurements. And this idea of an artifact as the standard of length rather than the human body caught on all around the world. In Europe, for example, every town would have cemented into the town square a length standard that would be used for commerce in that town. This is the town of Regensburg. It's got a pretty long fathom, as you can see. And the problem was that if you went into a surrounding town, you would get a different standard of length. So remember, I mentioned the French Revolution. The French Revolution brought us the metric system. It brought us a new unit of length called the meter. And the meter was defined to be 1/10,000,000th of the distance between the pole and the equator. Now, how do you do that? Well, you send out people to survey that distance. Well, they only went from Dunkirk to Barcelona. It took them several years. There was a war on, and they kept getting thrown in jail because they showed up in a town with a bunch of funny looking apparatus. And so people would throw them in jail until they decided that this was a legitimate scientific operation. They brought their measurements back with the intention of replacing the old definition of length with something based on the size of the earth. And this medal that was cast to commemorate the idea shows a mythological creature literally measuring the earth. But in fact, that is what they did literally. They literally measured the earth in terms of the old units, brought it back, and realizing that this wasn't a very convenient thing to do, to base things on the length of the earth, they made an artifact. This is the meter of the archives, and it became the standard of length for the country of France. A few decades later, the countries of the world got together to adopt internationally the metric system that had started in France and made a new meter bar that was 1 meter between 2 scratches on the meter bar. And that became the standard of length for the entire world. The trouble was that just as in the definition of the second, you soon had a technology, namely optical interferometry, that allowed you to measure lengths far better than you could measure using the scratches on a metal bar. You use a microscope to look at the scratch, and you try to figure out where the middle of the scratch is. And the scratch is several millionths of a meter wide, and your microscope can only resolve 1/1,000,000th of a meter. And you have these devices that use the wavelength of light as the standard of length. And if you move this mirror by just a couple of 100 nanometers, a few tenths of a millionth of a meter, it changes this interference pattern from having a dark spot in the middle to having a bright spot in the middle. And so it's easy to measure distances much less than a tenth of a millionth of a meter. And so people had to make their measurements using light. And what happened was that it became the de facto standard of length. The legal standard of length was still the distance between two scratches on a metal bar. But when people made measurements, they referred those measurements to the wavelength of light, and eventually they changed the definition. It took them until 1960, but they changed the definition of the meter to be a certain number of wavelengths of light from a krypton lamp, which is shown here. And when it's energized, it produces an orange light, and that became the new definition of the meter. But it didn't take long before people had lasers whose light was far more pure than the light from a krypton lamp, and started to use the laser light as the de facto standard of length. So this is a picture of a helium neon laser stabilized to a transition in molecular iodine, and that became, again, a new de facto standard of length, an unofficial standard of length. So by the time everybody was using this, people thought, oh, we need to redefine the meter again. And the obvious thing to do would be to define the meter in terms of this new laser standard that everyone was using as a de facto standard. But fortunately, they did not do the obvious thing. They did something that was far more brilliant, something far more beautiful. They defined the speed of light. We have this general expression that the speed of light is equal to the wavelength of the light times the frequency of the light. Remember, light is an electromagnetic wave. It has a frequency just like microwaves. If we define the speed of light, what it means is that anytime we can measure the frequency of any light, we know its wavelength immediately. So the new definition was that the meter is the length of path traveled by light in a certain fraction of a second. And this number is the speed of light in meters per second, because this is the way we define a meter. So this definition of the meter is equivalent to defining the speed of light. And it tells you anytime you can measure the frequency of any light, you immediately know its wavelength, and you can use that to measure length. Now, the beauty of this is that if somebody makes a better laser, and people did, if somebody devises ways of measuring the frequency, remember we talked about measuring the frequency of things, and they did devise ways of measuring the frequency better without counting, okay? Then immediately you know what the wavelength of that light is, and these improvements can be incorporated into the definition without changing the definition. So the beauty of this is that, I just want to point out, these guys, Jan Hall and Ted Hench, made better lasers, and they developed means for measuring their frequency using a thing called a frequency comb. So you take a mode lock laser that puts out lots of different frequencies. The spacing between those frequencies is at a microwave frequency that you can count. But the optical frequency itself is a multiple of that. So there's a connection. You can get the frequency, even though you cannot count it directly. You can get that frequency using this optical comb technique. So their work changed the definition not the definition. Their work changed the realization of the definition of the meter, but it was not necessary to change the definition. So here, what we have is an evolution from an artifact standard of length, the distance between two scratches, to an atomic standard of length, a particular atom, namely krypton, to something even more fundamental, the speed of light. So we're not tied to any particular atom. And so we should never need to change the definition again. So that's how the meter was changed. Now we're going to change the definition of the kilogram. And what we want to do is to change the definition of the kilogram in this same way by fixing a fundamental constant of nature. But before we go into how that is done, let's see if there's any questions about length before we go on.
So anybody, questions for Bill, or should we go ahead? Feel free to chip in.
I may have talked too fast in my attempt to make up extra time.
Not at all.
I'll try to go a little bit more calmly. Well, anyway, stop me if somebody comes up with a question in there.
Yeah, no, absolutely.
Okay, we'll go on to talk about. So we've had a short history of time, a brief history of time. We've had a short history of length. Now we're going to have a light history of mass. And just as with length, ancient people made artifacts, just like the ancient Egyptians made an artifact standard of length, the ancient Babylonians made artifact standards of mass, and here are some of those ancient Babylonian standards. The problem was the same problem we always have. Artifacts can change. Artifacts could vary from one place to another. The French revolutionaries wanted to fix that. And they wanted to fix it using this new standard of length, the meter, that was supposed to be the measure of all things. And so they devised a new standard of mass that's based on the meter. They said that this new mass unit, the kilogram, is going to be the mass of water that has a volume of 1 liter. And 1 liter is a cube, a tenth of a meter on a side. So you see the meter definition is part of the definition of the mass. And then we just have to make the right volume of water, and we've got our new mass standard. The trouble is that it's not so easy to do. Water, the density of water changes with temperature. It's not so easy to make exactly 1 liter of water. Water wets things. Some things it wets, some things it doesn't wet. You have a certain water in a container will have a meniscus, and that can make it difficult to determine what its volume is. So all these things made it hard to use this revolutionary definition. And so they did the same thing that they did when they made a new standard of length. They made an artifact. And here I'm holding this artifact in the archives of Paris. This was deposited just like the meter was deposited in 1799. And this little object here has a mass as close as they could make it to the mass of a liter of water. A few decades later, when the entire world got together in 1875, the Treaty of the Meter made the metric system the standard of measurement for the entire world, and they decided to make a new version of the kilogram. So out of platinum iridium, they made a cylinder as close as they could make it to the original kilogram of the archives. And this now became the kilogram for the entire world. And it's also the last artifact. The definition then, and up until just a couple of years ago, is that the kilogram is the unit of mass. It's equal to the mass of the international prototype of the kilogram. Now, I want you to think about this. It's the 21st century. The unit of mass is an artifact which was made in the 19th century. And it's based on an object that was made in the 18th century. That we are using 18th century technology in the 21st century is scandalous. Imagine that somebody left a fingerprint on the international prototype of the kilogram. All of us would lose weight by definition. This is intolerable. Well, nobody leaves fingerprints on the international prototype of the kilogram, but its mass changes just the same. Here is a plot of the mass of the copies that were made at the same time that the international prototype of the kilogram was made. They were all made identically. One of them was a little closer to the kilogram of the archives than the others, and it was chosen to be the international prototype of the kilogram. But the same process was used to manufacture all these kilograms, and then they were compared from time to time to the mass of the international prototype of the kilogram. And you can see they're all changing, and they're almost all changing in the same direction. Well, this might cause you to believe that, in fact, it's the international prototype of the kilogram that is changing, as well as all the others. But of course, it cannot change, because by definition, it is always a kilogram. Well, this is terrible. We have to fix this. It's scandalous. And we're going to fix it by the same technique that we used to fix the definition of the meter. There we defined a fundamental constant of nature, the speed of light. What will we do here? Well, to explain that, let me remind you of what is surely the most famous equation in all of history, that E equals mc squared. Now, there's another equation, not quite as famous. Well, first of all, what does this mean? It means that the total energy of an object is equal to its rest mass times the square of the speed of light. So the energy of an object at rest is its mass times the square of the speed of light. So you can see mass is in here. So that's why we're using this equation. Now, there's another famous equation, not quite as famous. It says that the energy of a photon, a particle of light, is equal to Planck's constant times the frequency of the light. In fact, this is the definition of Planck's constant. What does it mean? If I had some kind of a particle, like an atomic nucleus, and it emitted a photon that had a frequency f, then if I define h, and since I've already defined c, it means I know how much the mass of that nucleus changes. It's essentially weighing a photon. And since I can measure the frequency, and I've defined both Planck's constant and the speed of light, it means I know what that mass is. So all I have to do is measure the frequency of the photon, and I know what the mass change of the nucleus is in kilograms. Okay? Now, we don't actually do that. We don't weigh photons. We could, and we do, but we just cannot do it well enough, or at least not yet. So there's another trick, and that trick was invented by this guy, Brian Kibble. And it's a way of using an electromechanical device to realize that the new definition of the kilogram based on Planck's constant. So here it is. This movie is going to tell us how it works. So first, I want to remind you of how we weigh things traditionally. If I want to know what the mass of some unknown object is here, then I put it on a balance and I put known masses on the other side. You've all done this. And you keep putting known masses on the other side until the balance balances. And when the balance balances, then you say, I know what this mass is. It's equal to the sum of all of these masses. Okay, that's very standard. Now I want to invite you to think about another possible way of measuring the mass. Let's imagine that instead of putting known masses on the other side of the balance, that I put a coil of wire. And that coil of wire is immersed in a magnetic field. And the magnetic field exerts a force on the coil of wire. And if I can measure the current, and I measure exactly where the current goes, and if I can measure the field and exactly where the field points at every point on this this coil. In other words, if I know the direction of the magnetic field relative to the direction of the current, then I can calculate what the force is on that coil of wire, and I can balance that against the gravitational force that is on my unknown mass, and I'll know what the mass is. The trouble is that we cannot do those things. We cannot know this magnetic field well enough. So here's where the genius of Kibble comes in. Kibble said, fine, we can't measure the magnetic field well enough. Let's do something different. Take that same coil that we put current in to balance out the force of the unknown mass in the magnetic field, and take the leads of that coil and connect the leads to a voltmeter, and now move the coil in the field of the magnetic field, the same one that we used before to create a force. That's going to create a voltage, and we're going to measure that voltage. And we can measure the voltages very well. At the same time that it's moving, we measure the velocity of the coil, which we can also do very well. We call this the velocity mode. Measure the velocity, measure the voltage. The other part of the measurement we've already talked about. We put current into the coil, same coil, same magnetic field. We put current into the coil, and we balance the force created by that current being acted upon by the magnetic field. We balance that force against the unknown mass, and in this way, by making this measurement of the velocity and the voltage, we get all the information we need about the geometry of the coil. The mass of the unknown mass times gravity, which gives us the gravitational force, times the velocity that we measure in the velocity mode has got to be equal to the current that balanced this mass when we did the weighing mode, times the voltage that we got from the velocity mode. So this equation, which is true because mechanical power, force times velocity, has got to equal electrical power, current times voltage. This uses one measurement from the weighing mode and another measurement from the velocity mode on the one side of the equation, and the same thing, one measurement, the current from the weighing mode, times the voltage from the velocity mode on the other side of the equation. And now all we have to do is solve for mass, and it tells us what the mass is. But wait a minute. You say, you promised us Planck's constant. Where does that come in? Well, there's also the matter of gravity. We can talk about that later. But how does it relate to Planck's constant? And that's because the way in which we're going to measure the current and the voltage involve quantum measurements, the quantum Hall effect and the Josephson effect. Brian Josephson here, Klaus von Klitzing here, taught us how to measure voltage and resistance using quantum mechanics. Josephson said that if we had two superconductors in close proximity with an insulating barrier between them, that if we had a voltage across the junction, there would be an AC current that whose frequency would be given by the constant 2e/h in hertz per volt. And von Klitzing taught us that if we had a two-dimensional electron gas and put a current through it in one direction, that it would produce a voltage in the orthogonal direction, and that voltage would be quantized in units of h/e², which is the unit of ohms. So we use these two techniques to measure the voltage, which is now going to be proportional to h/2e, and to measure the current, which is going to have voltage and resistance in it. So the e's cancel out, and the mass ends up being proportional to Planck's constant, just as I promised. Well, here is a picture of one of the apparatuses at NIST that's used to do this. This apparatus, which you see is quite large, can measure a kilogram to a part in 10 to the 8th, which is better than the amount by which these kilograms are changing due to whatever dirt that gets on them we don't really know. But this is the way it's now done in some of the laboratories around the world. My colleagues at NIST are so confident in their measurement that they have tattooed the values of Planck's constant and the other constants into their forearms. So before we go on to the final part of this talk, let's see if there are any questions about mass or about length.
So, Bill, we have a question from the last part of the talk, because there's a small delay between our Zoom conversation and YouTube, and then when people asked, you had moved on. But then right. I'll tag the question now, and I'll tag along another that has to do with the kilograms. So the question was from Thiago, and he wanted to ask, what about that meter? Is it dilating? Is that one of the issues that was in people's minds when you redefine the meter? And the other question is, do you know why that standard kilogram in Paris, why these were varying? Is this, where is this coming from? Does anybody have an idea where that variation is coming from?
Okay, so let me try to answer both of those questions. It's true that the meter bar might change because of temperature, but the meter is defined when the ambient temperature of the meter bar is a certain fixed value. So there might be uncertainties about whether you've got just the right temperature. But I think that the main reason is that a scratch is just not a suitably precise definition of what you mean by a meter. To say that the meter is the distance between two scratches, where is the middle of the scratch? Somebody has to make a judgment about where the middle of the scratch is. And that may not be an obvious thing, and it may not be something that you can define very well. So, and it's so much more convenient to make measurements using the wavelength of light in an interferometer that the technology outran the definition. So that was the main reason why that you had to change the definition, was the technology had surpassed the definition itself. Now, there are other things that might happen. I don't know whether people in the 19th century knew this, but when you make a solid object, after it's made, its size can drift. We see this all the time in making optical cavities. They're made out of some kind of glass or some kind of ceramic, and you put mirrors on them, and then you shine light in, and you know that the light's wavelength stays constant, and you see that the length of the piece of glass is changing. It's because when you manufacture something, it's not necessarily in its equilibrium state, and it might take years to come to equilibrium. So this is another thing that's a problem with artifact length standards, and I don't even know whether people in the 19th century realized this. You needed 20th century technology to find that out. Okay, so that was the question about the meter. The kilogram, why is it changing mass? We don't know. What we imagine is that either it's collecting some kind of dirt. Now, there's a cleaning procedure. The mise en pratique for the kilogram says before it's a kilogram, you have to clean it in a certain way, and everybody is supposed to clean their kilograms in the same way. But do we know that the amount of dirt that's taken off of the kilogram when you clean it is always the same? Do we know that when we clean it, that we don't put extra layers of the cleaning substance on it? Do we know that the atmosphere that surrounds the kilogram is going to be the same all the time? So there may be different kinds of dirt. We simply don't know. And now that we have a stable definition of the kilogram, we might be able to find out about what is causing it, because we have something that we know stays put.
Cool. So we have before I pass on, Paulo has a question, but before I pass it on, I have a comment, just a comment on YouTube saying, "Hey, why didn't you get tattooed?"
Why didn't I get
tattooed like your colleagues there? Why didn't you get a tattoo of the
because I wasn't, yeah, because I wasn't part of the team that was making this final measurement. I started doing experiments that related to this in 1978. And I stopped doing those experiments in about 1988. And these guys were the ones who did the most recent ones. You see, when I was working on it, it was probably 2 orders of magnitude worse. And these guys took it to its present beautiful state.
Cool. So, Paulo, you have a question. Go on.
Maybe ask Claudio first. Claudio has a question on the chat.
That is true. Claudio has a question there. Claudio Lenz, he says, "Hi, Bill. Can you clarify about G in the definition of mass?
Yeah.
There, where you finish, one would be defining kilogram. Greetings from Claudio."
Right. So I assume what we're talking about is this G right here. The local acceleration of gravity. You have to know that, and you have to know it really well. And what it means is you're going to have to measure it right where you're doing the experiment. And you're probably going to have to keep measuring it because it changes. When the moon goes around the Earth and induces the tides, well, actually, it's the rotation of the Earth, but the tides change because they're timed because the moon going around the Earth. As the Earth rotates relative to the moon, then and relative to the sun, this changes the local acceleration of gravity. And you got to take all of that into account. Now, fortunately, those kinds of changes are pretty regular. So if you make your measurements for a long period of time, you can probably know what the acceleration of gravity is reasonably well at any given time. But if the water table changes, like if the groundwater changes, if it rains a lot, that's going to change your local acceleration of gravity. So you really have to measure it. Fortunately, we know how to measure it really well. So people can measure the acceleration of gravity to a few parts in 10 to the 9. And so since we can measure these kilograms to a part in 10 to the 8th, it's okay. And I think that if we need to know what the acceleration of gravity is better, then we'll probably be able to figure that out. And I should say there are 2 key ways of measuring the acceleration of gravity. One is you drop a mirror and you measure interferometrically the position of the mirror as it falls and extract gravity from that. The other one is you drop atoms and you measure a Doppler shift of their frequency response, and that works even better than dropping a mirror. So there's lots of well, not a lot. There's 2 main ways of measuring, and a lot of people have spent a lot of time perfecting those.
All right, Paulo, your question.
Bill, I'll try to be brief, but the whole game is to get rid as much as possible of any kind of systematic effect, any kind of artifact and things like that. When we're talking about mass, there are 2 ways to think of mass: inertial mass and gravitational mass. And there's an equivalence principle related to that. Shouldn't that guide the standard of mass?
Yeah. Well, it's funny to talk about that. I wonder, I haven't yet consulted a historian of science to find out when it was that people started to understand that there was a difference between gravitational mass and inertial mass. Essentially the legendary Galileo experiment with the Tower of Pisa. Today, we would interpret that as showing that gravitational mass and inertial mass are the same. But when did people even imagine that they might be different? at the level at which we have to worry about those things, I mean, we've tested that equivalence principle to levels that are on the order of parts in 10 to the 11th with things like Etvosh experiments. I mean, there are different kinds of experiments that can test the equivalence principle, but if you like the Etvosh experiments, then I think they work at about a part in 10 to the 11th. Since we can only measure mass at a part in 10 to the 8th, it's not yet an issue unless there are features that aren't exposed by the Etvosh experiment, and there may very well be, that we should have to worry about these things. So what are we measuring? I would say that in both the old definition and in the new definition, we're looking at gravitational mass because we use balances and we use forces to do these things rather than accelerations, which would be inertial mass. But because of Einstein's theory of relativity, these are closely connected. But what if Einstein's theory of relativity is wrong? And everybody thinks that it must be wrong because we can't make it consistent with quantum mechanics. And everybody thinks that quantum mechanics and gravity have to be unified at some point, and that's going to mean that we're going to have to modify Einstein's theory of general relativity. But nobody's ever found anything wrong with it experimentally. So we're in a situation where we just don't know. And I think this is one of the great adventures of our current era, is to try to figure that part out. And who knows, maybe these kinds of measurements will give us a clue as to what we're going to have to change. But I think we're probably going to have to do better than a part in 10 to the 8th.
So Bill, I'll put up two questions for you and then we can move on. Otherwise, we will keep you here forever. So one of the questions was related to this, was from Lucas on YouTube, and he was asking about what about do you need to have the object at rest for the definition there of the mass using mc squared? And then he elaborated on that, saying, even if an object is at rest, its constituent parts may not be. And then if they are made of different materials, they might have different components and momentum, and the temperature may get into play. How is that? Is there any auxiliary definition for mass when you make those experiments, connecting Planck's constant with the mass and so on?
Yeah, so those are very good and deep questions. And the answer is that we just ignore all of those things. That is, the fact that the constituent particles of of a standard piece of a standard kilogram are moving are things that we simply ignore. It's true that if the temperature changes, the mass is going to change, because for just, at the very least, for that reason, there's less energy if the thing is colder. So obviously it's going to have less mass. Those effects are pretty small, and we specify in the mise en pratique what the temperature is. But if you really want to be careful, you would have to consider all of these things properly. And, it's just like our definition of the second and where the clock is. If we want to be very careful, we have to specify all those things, and we do in principle. But the better we get, the more important these things are, and the more difficult it is to be completely precise about what we mean by mass or what we mean by time. So the answer is, for the moment, we're not worried, but we may have to worry.
All right. So for one last question for now, and then I'm sorry for the many other questions that people are asking. I'll try to keep them to the end. Now I'll pass it over to Alinka. Alinka, please turn on your mic and ask your question.
My question is, I'm a nuclear physicist, and in nuclear physics, we measure masses of nuclei and ions in Penning trap with a precision of 10 to the minus 10. Yeah. So can these not be used to define, because frequency, as you said, is what we can measure the best. can we not put the mass in terms of frequency as we do it when we measure?
Yeah, and the answer is yes. In fact, it's a perfect lead into my next slide. So there's another way of measuring mass using Planck's constant. So imagine that I've got an atom and I shine a photon in, and the atom absorbs the photon, goes to its excited state. Because the photon carries momentum, it'll cause the atom to recoil. So the atom will now be moving with a velocity that depends on its mass, on Planck's constant, and on the wavelength of the light. Planck's constant is defined. The wavelength of light is easily measured. So if we measure the velocity, we know the mass. We know the mass of the atom in kilograms, okay? Now,
Yes.
Here's where the comparison that you described comes in. With these ion traps, you can compare nuclear masses to parts in 10 to the 10. What you're doing is comparing one mass to another by comparing their frequencies in a penning trap. What you're not doing is measuring what the mass is in kilograms. You're measuring what the mass is in, say, atomic mass units. This experiment tells you what the mass of some atom is in kilograms, not in atomic mass units. So now you use these wonderful techniques that you have to compare the mass of this atom, typically rubidium, to the mass of some other atom that's much more useful, like silicon. So you make a penning trap comparison. Well, I mean, it's a little bit more complicated. You make carbon compounds of these things so they nearly have the same atomic mass, and you compare them, and then you find out what the mass of a silicon atom is, and you'll see why silicon in just a moment, is in kilograms by comparing it to the mass of rubidium in kilograms using these wonderful and very accurate ion trap measurements. The reason you want silicon is we can make perfect crystals of silicon. So you make a perfect crystal of silicon, turn it into a perfect sphere. This is the most spherical object ever made by humankind. And because it's a perfectly spherical object, you can measure it. And because it's a perfect crystal, and because you can then measure the lattice constant by X-ray interferometry, you can essentially count how many silicon atoms there are. And because you know what the mass of the silicon atom is in kilograms, having done the ion trap comparison, you now know what the mass of this object is in kilograms. It's not too useful to know what the mass of a silicon atom is. What you need to know is what the mass of a macroscopic object is. And now you have both. You've got the mass of the silicon atom in kilograms, and by extension, the mass of everything that you measure in your ion traps is now known in kilograms, not just in atomic mass units. And then, because of this perfect crystal of silicon, you can make this thing equal to a kilogram and use it to measure macroscopic masses. So this is another way of measuring the kilogram. Of course, before you define Planck's constant, doing this measurement is a way of measuring Planck's constant. So people used this way of measuring Planck's constant. They used the Kibble balance way of measuring Planck's constant. And when everybody around the world agreed on what Planck's constant was, then they defined Planck's constant, and that now becomes the definition of mass. And the beauty is it doesn't tell you how to do it. It says however you want to do your measurement of realizing the kilogram using the definition of Planck's constant, that is good. So now here's laboratories all over the world that have agreed on Planck's constant. And once that happened, then in 2018, in Versailles, the countries of the world got together and agreed that they would fix the value of Planck's constant and use that to define the kilogram, as well as the ampere, the mole, and the Kelvin, by defining the charge of the electron, Avogadro's number, and Boltzmann's constant. And at that meeting, after 60 countries of the world unanimously agreed to do that, they showed this movie. Sorry. Oh dear. Okay. Now I seem to not be able to play the movie. There we go. I'm so sorry. Okay, now it's playing. This is what they showed after they all agreed.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world scientific community.
At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. But
We did it.
Ce l'abbiamo fatta.
Wir haben es geschafft. Lo logramos.
Neyse Boli.
我们做到了. Biz buna nail olduk. Proud of die.
Biz bunu жасадық. Het is ons gelukt.
We сделали это.
انتصرنا. Vi gjorde det.
Amerika.
Mi smo to učinili.
Dokázali jsme to.
Angažnaha.
سويناها.
Congratulations. 축하합니다. Felicitaciones.
Mazal tov.
Congratulazioni.
Shate Ralelovicia.
Selamat sukses.
Parabéns.
Ongela. Omedeto.
Amguida.
Onneksi olkoon.
Mabruk.
Kapai.
Aiko.
Félicitations. Congratulations.
So the fact that 60 countries could unanimously agree on anything gives me a little bit of hope that perhaps the world can come together on other issues. I haven't said very much about the ampere. The ampere is now defined by defining the charge on the electron. So the ampere is a certain number of electrons per second. The mole is now, instead of being an amount of substance that has a number of entities equal to the number of carbon-12 atoms in 12 grams of carbon-12, it's just a number. We have defined the Avogadro constant. And finally, the Kelvin is what we use to define, well, that is, we've defined the Kelvin by defining the Boltzmann constant. So instead of a Kelvin being 1 over 273.16 of the triple point of water, now the Kelvin is defined by defining the Boltzmann constant. So temperature, the temperature scale is now fundamentally microscopic. It has to do with the thermal energy of the microscopic constituents of a substance. And so the French Revolution brought us the metric system. The convention of the meter brought us an international acceptance of the metric system. And now all of the base units of the international system of units are defined by fixing the values of the fundamental constants of nature. Now you can have the international system of units on a wallet card. And it really appears that we've realized the dream of these revolutionaries to have a system of units that is good for all time and for all people, except, it seems, for time itself, because time is still tied to a specific atom, cesium, rather than to a fundamental constant. And what that means is that when we have better atoms than cesium, and we do, as one of the questioners asked about, we do have better atoms than cesium, that we're going to have to redefine the second. And my guess is that sometime in the next decade, we will redefine the second based on an optical frequency standard, an atom with a transition in the optical region of the spectrum. And what exactly that will be, well, only time will tell. So thank you very much. And I'm happy to take even more questions.
Let's all turn on our microphones and then thank you. Thank you for this wonderful.
Thank you very much.
I wanted to give you a standing ovation.
Yeah.
Thank you,
So,
Paula.
Let me finish. Let me start here with a question that was asked on YouTube, which is basically how you ended things. So, for the most part, we have fixed all standards of measurements for all time. Nothing will ever change again, except perhaps for for the second. So in that little table you showed there, that number actually has a small error bar in there somehow, somewhere.
Well, it doesn't. It doesn't have a small error bar. There's no error bar on this number. It's just that our ability to turn this definition into time, that is limited by the fact that the frequency is so low and the cesium atoms collide with each other and all these things that make it hard. So it's not that there's an error bar in the number. It's just that we don't know how to use it because cesium is not the ideal atom.
Perfect.
Just like there wasn't any error bar in what the distance between the two scratches were, we just don't know what that meant to be the distance between two scratches.
Right. So we have lots of people saying thank you on YouTube, and then there are some other questions here that I may ask, and people feel free to raise your hands. We can still abuse Bill for a couple of minutes more. So let's see here. So there is a question here by let's see here, by Carlos. Carlos is asking the following question here. He says, if you define mass itself, and we know that in particle physics, mass is tied up with this particle called the Higgs boson. So isn't that somehow, aren't you somehow tying the definition of mass to the Higgs boson? So that was Carlos's question.
Okay. And the answer is, I don't know. I don't know enough about the whole idea of how the Higgs boson gives things mass. One of the things I might point out, though, is that the Higgs boson gives mass to fundamental particles like quarks and electrons and muons and tauons. Most of the mass, or so my particle physics colleagues tell me, most of the mass of things like protons and neutrons, the kind of things that give us mass, have to do with binding energy, not with the Higgs mechanism. So the answer is it's even more complicated than that. It's not just the Higgs boson. It's the binding energies that result from the nuclear forces, which are really strange, because the binding energies go the wrong way. The usual, when things are bound, they have less energy. Well, these things have more energy because of the strange nature of the nuclear forces. So yeah, it's really weird, and I don't understand it myself at all.
All right. So Paulo, you have your hand raised. Go ahead.
Yeah. I'm also going to provoke a little bit, Bill. At the end of the 19th century, Michelson said that all of physics was essentially known, and that discoveries would be beyond the 6th decimal place. So now you're talking about measurement of time beyond the 18th decimal place. Can you tell us a little bit about, whether this is just, well, of course it's not, but why this is not just precision as a goal in itself, what that kind of precision is actually telling us, the new things about the universe that we're learning from those things. Why do we have to measure time, the second within 10 to the 18th?
Yeah. Okay. Beautiful. So, of course, Michelson was famously wrong because at the time he made that statement, we were on the verge of some of the biggest revolutions in our understanding of physics to have ever happened, partly related to the kinds of things that Michelson had done. Michelson, we often think of the Michelson-Morley experiment, which maybe and maybe not motivated Einstein to come up with special relativity in which the speed of light is always constant. Michelson always thought of that experiment as a failure, that he had failed to see the motion of the Earth through the ether. He never thought of it as being a breakthrough that opened up a whole new area of physics. And so I think it should give us a certain degree of humility that someone as amazing as Michelson completely missed what was going on in physics. So let's talk about finding, physics in the next decimal point. When people did really high precision spectroscopy of the hydrogen atom, they found out there were some funny things going on in the fine structure of hydrogen in the first excited state, in the 2p state and the 2s state. There was an anomaly, and that anomaly turned out to be the Lamb shift. And the Lamb shift opened up a whole new understanding of the way in which the vacuum changes the nature of physics. And today we now understand that the vacuum is not empty, that the vacuum is a seething, boiling pot of particles coming in and out of existence, and that we better understand physics, including that feature, or we won't understand what's going on. But where did that come from? That came from, or at least was verified by looking at very precise changes in the spectrum of atoms. Now, what can we expect for the future? That was really your question. What about the future? What will we get from having clocks that are this good? And the answer, as you well know, is amazing things. Because if we have two clocks that are operating with different atoms as their tickers, and if those atoms have a different sensitivity in their transition frequencies to something like the fine structure constant, or the ratio of the mass of the electron to the mass of the proton, which would be more likely in molecules, for example. So if you compared a molecular clock to an atomic clock, or two different atomic clocks, two different molecular clocks that depend upon certain fundamental constants in different ways, if we set those two clocks next to each other on the laboratory bench and see whether the ratio of those frequencies changes with time, that's going to imply that something like the fine structure constant, or the ratio of the mass of the electron to the mass of the proton, is changing in time. If that's true, that's going to change everything, because everything we know about physics assumes that those things are constant. So if they're not, we're going to have to rethink physics. Another possibility is take those two clocks and put them into a satellite with an eccentric orbit. Einstein says the ratio of those two frequencies has to stay the same regardless of where we are in the gravitational potential. But if the equivalence principle is wrong, which seems to be, the most fundamental piece of general relativity, if it's wrong, then general relativity falls apart. And we could test it at a level never possible before by using these clocks that are good to a part in 10 to the 18th, or even a part in 10 to the 20th today, with new advances. They're getting things that are good to a part in 10 to the 20th. I mean, who would have thought? I mean, just in a matter of a few years, going from a part in 10 to the 18th to a part in 10 to the 20th, just by being more careful about these these optical lattices, and having brilliant people like Anna Maria Ray and Junyi doing these experiments. So it's just, we live in a really exciting time.
So Bill, I'll ask the last question before we let you go, before we suck everything, every last drop out of you. So it's from Mateus online on YouTube, and I'll try to summarize. His question is related to your first provocation there. He's saying, basically, how can it be that Planck's constant can be used to make measurements of all matter in the universe? How can this be using light as a measurement of weight? And this seems to be kind of connected with your first provocation there, with if H, E, and C are defined, doesn't that define the fine structure constant, right? So what's going on in there?
Well, okay. So it may be related to a previous question that I had of how can we define C? Doesn't nature define C? Didn't God give us what C is? How can we human beings say what C is and define it to be a certain number? And the answer is that for any constant that has units, the value of that constant depends on what we decide those units are. So if we change the definition of the meter, then we change the numerical value of what a constant, any constant of nature that has meters in it is going to be. If we change the definition of the second, we will change the numerical value. Remember, the numerical value, the actual value of the constant is equal to the numerical value times a unit. If we change the unit, we're going to change the numerical value because the constant itself is somehow, idealized idea of what the constant is. Presumably that's a constant. Now, the fine structure constant doesn't have units. So we can't define the fine structure constant. It's the thing that's given to us by nature. Okay? Now, most of us have been taught to think of the fine structure constant as being E squared over H bar C, but it's not. In SI units, it's E squared over 4 pi epsilon naught H bar C, where epsilon naught is the electric permittivity of the vacuum. And in the old SI, before May 20th of 2019, epsilon naught was fixed because the speed of light was fixed and the magnetic permeability of the vacuum had been fixed ever since the old definition of the ampere came in. The definition of the ampere that has to do with forces between wires effectively defines what we mean by mu naught, the permeability of the vacuum. Well, if you've defined mu naught and you've defined C, then obviously you've defined epsilon naught because C is related to epsilon naught and mu naught, okay? So before 2019, mu naught was fixed and E and H were not. So think about this. If you had done an experiment and found that the fine structure constant changed, and you did the experiment before 2019, then you would conclude that either E or H or both of them changed because C was defined and epsilon naught was defined, okay? But if you did that same experiment after 2019, then you would have to conclude that epsilon naught changed because all the other things were defined. So obviously that means that it doesn't make any sense to talk about whether some quantity, some constant that has units changes with time. The only thing that makes sense to talk about is unitless constants, like the fine structure constant or the ratio of the proton and electron mass, or any number of other dimensionless constants that set the strength of the weak force or the strong force or the ratio of those forces. Those are all dimensionless constants that it makes sense to ask the question, do they change with time? But it doesn't make any sense to ask whether H changes with time because today it's illegal for it to change in time, okay? So it just doesn't make any sense. If I can say that silly statement that it's illegal for H to change, then it obviously means that it's nonsensical to talk about it changing. I like to tell students who have done an experiment where they measured the speed of light that they didn't measure the speed of light because it's illegal to measure the speed of light, or at least it's illegal to have it change. What they were doing instead was they were realizing the meter. They were calibrating their meter sticks. They weren't measuring the speed of light.
Wonderful. So I think we are almost coming to 2 hours here, and I think we can leave other questions. I can collect the questions and send it to you, or we can then review them in the chat later. But I think it's about time that we close. So I ask for people to, if they want, turn on their cameras and their microphones. And let's thank again Professor Bill Phillips. This wonderful, wonderful talk.
Thank you very much.
No, we thank you. It was absolutely wonderful,
Yes.
both the chat with our students and now this talk. Paulo, do you want to say some last words before we finish here?
Yes, I would like to thank you very much for the opportunity to talk to you. I think it was Bill, thank you so much for this enormous privilege of having you and of discussing so freely with you, asking you so many questions. It was just delicious, and I'm very happy that we will have this on YouTube for other people to see afterwards. So thanks a lot.
Well, thank you. Thank you for your questions, for everyone's questions, which have made this a really lively time. And I think your questions in particular have exposed how much we don't know, and therefore how exciting it is to be a physicist right now.
Good. So everybody, thank you so much. Thank you, especially Bill, and until the next time. All right. So now we are closing down. Thank you, Bill.
Thank you.
Bye.
Thank you, Bill.
Bye.